So Jai Hind, students, in the last lecture we have discussed about the um, working of the half wave rectifier, working of the center tapped full wave rectifier. Also we have discussed about the parameters of the half wave rectifier, where we have already calculated the DC value of the output waveform of the half wave rectifier, that is the average value, the root mean square value, the ripple factor, and the efficiency. So now we are going to discuss now the various parameters of the full wave rectifier. So full wave rectifier, first of all, let us calculate the root mean square value. So root mean square value, as we can see, because in case of the full wave rectifier, the output of the waveform is this. So here we can see that the signal is repeating after the pi only. We are having the same signal during the time period or during the span 0 to pi, and again the signal is repeating the pi to pi. That means here our interest will be lying only for this, because after that the signal is repeating, and that's the reason here in the base we are having only pi, and also we are integrating the value from 0 to pi instead of writing here 2 pi as we did in case of the half wave rectifier. Okay, so again putting the formula for the cos 2 theta to replace this square sin square omega t term. So we replace that value by 1 minus of cos of 2 omega t by 2, and now integrating this term and placing the limits, we calculate the value of the VRMS, and that comes out to be Vm by root 2. It was Vm by 2 in case of the half wave rectifier, whereas it is Vm by root 2 in case of the full wave rectifier. Now coming to the average value, again the average value, the area under this curve and divided by the base value, that is pi. So it is Vm by pi 0 to pi sine of omega t d omega t. Integrating this and placing the limits, we get the VDC, that is twice of Vm by pi, whereas it was in case of half wave rectifier, it was only Vm by pi, and in this case it was Vm by 2. That was for half wave rectifier, and also this is for half wave rectifier. So here you can compare the two parameters, Vm, VRMS and VTC, or the V average. Next is the ripple factor. So again we know that the ripple factor is the ratio of the VAC by VDC. What actually ripple factor? Ripple factor is nothing but the it can be defined as the measure of the AC components that are being superimposed on the DC component. That means how many AC components are present on the DC output, and the this factor, if this value is large, that means there are so many AC ripples are present, and if this value is less, that means the less AC ripples are present. So lower the value, better is the performance of your device. So here we can see that VRMS is VRMS is nothing but the it is having both the component, DC component as well as AC component. So VRMS is equal to square root of the DC square plus AC square. So here we can calculate from this equation. From this equation, we can find out VAC is equal to under root of VRMS square minus VDC square. And if we keep this value in this and taking out your keeping in this equation and taking out your VDC, if we divide the whole equation by VDC here in this case, so we get the formula of the ripple factor, that is under root of VRMS by VDC square minus 1. And this we know that in case of full wave rectifier, the average value of the full wave rectifier is 2 Vm by pi, and the root mean square value we have already calculated in the previous slide, that is Vm by root 2. So placing these two values in this formula and solving this, we get the ripple factor, that is 0.48, whereas this ripple factor was 1.21 in case of half wave rectifier. So here you can see that because the ripple factor is less in case of a full wave rectifier, which is 0.48 only, and it is very high in case of half wave rectifier, that is 1.21. That means the performance of the full wave rectifier is superior than the half wave rectifier, because there are very less number of AC ripples are present in case of the full wave rectifier. Next is the power and efficiency. So what is power? Power is nothing but the you can say that power is V into I, and or you can say it is I square R. So here we know that in the center type bridge rectifier, during the we can say that input voltage is VAC and output voltage is VDC. So here we can say that PAC is VAC square or IAC square IAC square by R RL plus RF. RF is the forward resistance of the diode and RL is the load resistance. So the total resistance which is appearing in AC is both the two resistances, that is RF and RL. Here we can see. So it is PAC is nothing but the root mean square value multiplied by this is basically the RMS value, you can say, and multiplied by the resistance. So square of the current multiplied by the resistance, that will give you the AC power, whereas DC power is what? The voltage which is appearing across this is DC. So you can say that the DC current, PDC is equal to DC current square plus load resistance RL, because the output voltage is measuring across the load resistance only, and that's why this forward resistance will not come into the picture. It will be there only in case of the AC power, or you can say the RMS value of the current will be appearing in case of the AC power only. But we can say that the value of RF is far less than RL, so neglect this value, and if we neglect this value, then the resistance, this will be removed, and you will be having the value that is equal to, if you are neglecting this value, then RL will get cancelled, and solving this we get the efficiency that comes out to be 81.0%, whereas in case of half wave rectifier it was only 40.6% that we have calculated in the last lecture. So here again we can see that efficiency just 50% in case of half wave rectifier in comparison to the full wave rectifier. So if you compare all the parameters of the half wave rectifier and full wave rectifier, then we can say that full wave rectifier has better performance in comparison to the half wave rectifier. Now coming to the next circuit, that is the bridge rectifier. This is the another type of the full wave rectifier. The difference between the center tapped and the full wave rectifier, this we are going to discuss today. Here the first difference we can see that the circuit diagram that is different. In case of center tapped full wave rectifier, we have the center tapped transformer and 2 diodes and 1 load resistance. Whereas in case of bridge rectifier, we don't need any center tapped transformer. So this is one advantage of the bridge rectifier over the center tapped full wave rectifier, because the fabrication of the center tapped transformer is difficult, and the number of secondary windings must have the because the center of the secondary winding is being tapped, so the number of windings across the first half and second half should be exactly equal to have the accurate result. And because of this, the cost of the transformer is also high. So this is the one difference of the bridge rectifier and the center tapped rectifier. And another difference is we are having the 4 diode in the circuit, but it does not affect the cost of the circuit much, because the diodes are very cheap components in comparison to the center tapped transformer. Center tapped transformer is a very costly device. So these are the first 2 differences between the bridge rectifier and the center tapped full wave rectifier. Now, let us first of all discuss the working of the bridge rectifier. So here we are having the 4 diodes, and it is very important to note that the direction of the diodes which are present in the parallel arm are same. So here, during the first half cycle, 0 to T by 2. So diode 0 to T by 2. This is terminal A and this is your terminal B. So terminal A will be at positive potential and B will be at negative potential. So this will make diode D2 forward bias, and also this makes diode D3 forward bias, but this negative terminal makes diode D1 and this positive will make diode D1 and D4, both reverse bias. So this is open circuit. This is also open circuit. Whereas these 2 diodes D2 and D3 will be forward bias and offering 0 resistance. So if this happens, we can see the circuit will look like this circuit. So here we can see that the direction of the current will be flowing from this, because current flows from higher potential to the lower potential. So the current is flowing in this direction like this and moving through this load resistance and passing through the second resistant diode and coming out. So this is the direction of the current through the load resistance in the first half cycle. So because this was at the resistance, this terminal of the resistance is at higher potential and this lower, and due to the direction of the current, the output voltage, this terminal will be at higher potential and this terminal will be lower potential. That means the direction of the current is same. So that's why we are having the output is in the we are having the positive voltage at the during the first half cycle. Now, in the second half cycle, during the T by 2 to T time period, this terminal A will be at negative potential and B will be at positive potential. Now, because of this voltage polarities, now your diode D1 will be forward biased. Also, diode D4 will be forward biased, but diode D3 and D2 will be reverse biased. So, reverse biased, forward bias and forward bias. So, in this case, your equivalent circuit will look like this circuit. And this is minus and this is plus. So, again, now current is again flowing from the higher potential to the lower potential. So, now the current direction will be like this, and across this again, we can see in both the cases, the direction of the current through the load resistance is same. That means in the negative during the negative half cycle, that is the second half cycle, again the direction of the current will be same across the load resistance, and that is how we get the output voltage that is unidirectional. The bidirectional signal has been converted into the unidirectional. Now, this is very important to notice in both the half cycle. Here we can see during the first half cycle, that is the positive half cycle, we can see that the voltage which is appearing across this is Vm. And this diode is open circuit and this diode is open circuit, and this is plus and this is minus. So, if I measure the voltage across this diode, the voltage appearing across this diode is equal to what? It is the diode was connected in this direction. So, we can see that the voltage appearing across this diode is equal to Vm, but it is a reverse voltage because positive voltage is connected to the negative terminal and negative voltage is connected to the anode of the diode. That means the voltage appearing across this diode is Vm, that is the reverse voltage. And similarly, if we measure the voltage across this diode, again the direction of the diode was like this in the circuit, in the original circuit. So, again the voltage appearing across this diode is also equal to Vm, but this is the reverse voltage, negative in magnitude. Magnitude is Vm, but the polarity is negative. This means that in both the in the first half cycle, both these two diodes which are in the reverse bias state, they are facing a reverse voltage of the magnitude Vm. That means the peak inverse voltage of the bridge rectifier is Vm. Similarly, if you come into the negative half cycle, you can see that the voltage across these two diodes, if we measure this voltage, it will be equal to again Vm, but this is plus and this is minus, and our diode is connected like this. Diode was connected like this. So, again, this positive is connected to the cathode and this negative is connected to the anode of the diode. That means this is again a reverse voltage. So, in one half cycle, these two diodes are facing the reverse voltage Vm of the magnitude Vm, and in the negative half cycle, the another two diodes are facing the reverse voltage, that is Vm. So, the peak inverse voltage is Vm in case of the bridge rectifier, whereas it was twice of Vm in case of the full wave, center tap full wave rectifier. So, here you can see the difference, which one is the better. Of course, the bridge rectifier is better because in every half cycle, the diode is phasing only the maximum reverse voltage, that is Vm, whereas in center tap rectifier, it was 2 Vm. So, the because reverse voltage may cause the breakdown of the diode will takes place, because peak inverse voltage is what? It is the maximum reverse voltage that a diode can withstand before breakdown takes place. So either you have to put some diode which is having the specification, that is the peak inverse voltage is very high, so that makes your diode expansive. Or if you are using the same diode in the half wave, in the center tap rectifier or the bridge rectifier, if having the same specification, then of course the bridge rectifier is better option than the center tap rectifier. So there are the two reasons of using the bridge rectifier over the center tap rectifier. One is the peak inverse voltage, that is only Vm in case of bridge rectifier, and like your center tap rectifier, that is twice of Vm in case of center tap rectifier. And also in center tap we have to use a center tap type of transformer, which is an expensive and difficult to fabricate, whereas here we use the ordinary type of the transformer, which is very cheap in comparison to center tap type of the transformer. So here is the comparison. We can see that the half wave rectifier, bridge rectifier and center tap rectifier. So half wave rectifier, the DC value is only 0.318 Vm. But if we use practically that value, if we calculate that DC value, then this Vm minus 0.7, because 0.7 is the barrier potential of the silicon type of diode. So here we are considering the silicon diode, and we know that in comparison to the silicon and germanium, we use preferably silicon is preferred over the germanium because of the various advantages. That is, it has low leakage current, high breakdown voltage, less temperature sensitive, and the cost and the availability of the silicon is very high in comparison to germanium. So these are the various reasons. That is why we preferably use the silicon over the germanium, and that's why we have considered here also the silicon parameters. So here in the bridge rectifier, because two diodes comes into the picture at a time, so this this voltage will be 1.4. So the DC voltage is slightly lesser than the DC voltage which appears in the center tap rectifier, because here only one diode comes into the picture at a time at every half cycle of the input signal. So this is the comparison of the three rectifiers. So here we can see this is one numerical of the center tap bridge rectifier. Here we can see we have to determine the output voltage for the network and calculate the output DC value of this signal. So here we can see during the positive half cycle, input signal is giving 10 volt maximum value, and peak to peak it is 20 volts. So during the positive half cycle, diode, let's say this is your diode D1 and this is your diode D2. So diode D1 is in a forward bias state and diode D2 will be a reverse bias state. So if we see the circuit will look like this. And here if I draw the equivalent circuit, so it will be, here we can see these two resistances are coming in parallel, and here across this resistance we are measuring the output voltage, and these two are in series, and across, and this series combination of these two resistances in parallel with this 2 kilo ohm resistance. Here we can use the, because the voltage which is appearing across this is equal to 10 volt, the maximum value 10 volt. So if you want, I want to calculate the voltage across this load resistance RL, then we can apply the voltage divider theorem. Let us say this is your R1 and this is R2. So I can say this is R2, this is R1, and this is your RL. So by applying the voltage divider theorem, we can say that the voltage RL divided by R1 plus RL times VI. So that will give you the voltage, that is V0. So if you place this value, we can say that output voltage will be equal to 5 volts, and that is the maximum value. So this is your 5 volts, and if I would like to calculate the average value of this, then that will be equal to 0.636 times of the maximum value. So that comes out to be 3.18. So this is the DC value of the output waveform. So this is all about the rectifier circuit. In the next subsequent lecture, I am going to discuss the special type of the diode, that is the Zener diode. So in the forthcoming lecture, I'll be discussing about the Zener diode. Zener diode is a special type of PN junction diode, which are used for the voltage rectification. So how do we use that diode as a voltage rectifier? That we will be discussing in the next lecture. Rectifiers are the diodes which are highly doped PN junction diode and which operate in the reverse bias condition. If you connect that Zener diode in the forward bias condition, then it behaves as a normal PN junction diode. But if we connect that diode in the reverse bias condition, then it act as a voltage regulator. So this is all about today's lecture, and see you soon in the next lecture. That is the Zener diode as a voltage regulator. Thank you. Jai Hind.